We're going to start out by looking at an example with a first order system. We're going to come back later and look at generalized systems for both first and second order, but we're going to start here to hopefully sort of ease everybody into this idea. So first of all, what do I mean when I say order? First order, second order, what is that? So as I have written here, order of the system is either the order of the equivalent differential equation and either way you want to think about it, we can talk about the order of the denominator polynomial of the transfer function. And so oftentimes, particularly in this class, that's going to be a lot easier for us. So we're going to be focusing on the order of the polynomial in the denominator. And of course, that's after canceling any common terms. So for this example, we're going to consider this system here. So we have some transfer function, which is first order. So in our denominator, we have s to the power of 1 is our highest order. If we had a s squared, it'd be a second order transfer function. And then let's also put an s plus 2 in the denominator. So this is our transfer function of our system g of s. So of course, this system can have some input and some output. Otherwise, it's not a very useful system. So this is r of s for our input and c of s for our output. So one thing that we can do to characterize our system is we can actually plot this in something called our S-plane or a complex plane. And we'll come back to this and use this very frequently later on, but just to sort of introduce the idea right now, we have our S-plane, and as I said, this is a complex plane. So we have our sigma axis or our real axis and our j omega or our imaginary axis. And so in this case, we have a 0 at s equals -2 and a pole at s equals -5. And again, those are the locations that make the transfer function 0 and infinite respectively. So the way we can represent that on this S-plane, on this plot over here, is we can come in and at -2, so let me go ahead and indicate here is -2, and let's say here is -5, so not necessarily to scale. But what we can do is at -2 we place a circle, an open circle, and that is a 0. And at -5 we put an x, and that represents a pole. So again, this is sort of a representation we're going to use a lot going forward. So we could see that instead of our block diagram over here and know immediately where our poles and zeros are, and therefore what our transfer function looks like. So now coming back to sort of this polynomial description of our transfer function here, we can say, let's give our system an input. So an input of r of t is equal to u of t. So this is a step input. So that corresponds to r of s equal to 1 over s by taking the Laplace transform. And so this is what we call a unit step input. And so another bit of terminology is that the output is then our unit step response. And so it sort of makes sense in terms of if you think our input is a step input, so our output is a response to that input, so unit step response. So we can go through the analysis and we can see, as we have said before, c of s is in general equal to r of s times g of s. So in this case, that gives us s plus 2 in the numerator divided by s times s plus 5 in the denominator. Well, we can use partial fraction expansions to factor that out, and it turns out that we get 0.4 over s plus 0.6 over s plus 5. And again, that was from partial fraction expansion. The reason we want to do that is then we can go to our Laplace transform table and known pairs, and we can figure out what our unit step response is, c of t, and in this case it's equal to 0.4 plus 0.6 e to the minus 5t. And in this case, as I've mentioned in a previous video, our u of t is just going to be implied. So oftentimes that's the case with this textbook. So there's an implied u of t that's multiplied by all of this here. But oftentimes that's not explicitly shown, so I'm going to sort of follow the textbook's example and not explicitly show that here. So bringing this back to our terminology from the previous video, we can identify our forced and our natural response. So this 0.4 is our forced response, and this 0.6 times this decaying exponential is our natural response. So looking at this function and comparing it to sort of our C of S and where that came from, which part came from our transfer function, which from our input, we can make a couple important observations. So let me actually just bring this down here so I have some more room to write below it. So we can kind of keep an eye on this as we write here. So a couple things to note. So first of all is that the pole of our input function is generating the form of our forced response. So pole of the input is dictating the form of our forced response. And so I'll scroll up a bit and we can see what I mean by this. So forced response, pole of the input. So of course here's our forced response is 0.4, and we see the form of that comes from our input, which was this S here. So it's because of this S that we had this 0.4 over S, which ultimately became 0.4 when we took the inverse Laplace transform. Okay, so that's one observation. A second observation is that the pole of the transfer function is determining the form of our natural response. So pole of transfer function is dictating the form of our natural response. And again, this is just form, not necessarily the exact natural response. So again, here's our natural response, this 0.6 times the decaying exponential, which we know came from this 0.6 over s plus 5. And ultimately, that 0.6 s plus 5 came from this transfer function here, where we had our s plus 2 over s plus 5. Okay? Again, that's just the form of the transfer function, or the form of the natural response, excuse me. Now, a couple other things is that the pole on our real axis is generating that decaying exponential. So pole on our real axis in that plot in our S-plane above is generating that exponential response. So e to the minus alpha t, where our negative alpha is our pole location. So pole on the real axis gives us this decaying exponential. And so in particular now we're looking at this e to the minus 5t, and what we're saying is because we had this pole at negative 5, that means we're going to have an e to the negative 5t in our natural response term. Okay, and then one final observation we can make here is that the amplitudes of both our forced and natural response are due to both the input and the transfer function. So amplitudes of forced and natural response are due to zeros and poles of the input and our transfer function. And so the main takeaway here is that this amplitude of both of these types of responses are due to the input and the transfer function. And so basically what we're talking about here is the 0.4 and the 0.6. And so we kind of glossed over this by not going through the steps of this partial fraction expansion, but essentially in solving for this 0.4 and this 0.6 value here, we had to account for what the zeros were of our transfer function. In this case, we didn't have any zeros in our input, but we would also have to account for those, as well as poles of our input and poles of our transfer function. So all of those things combine to determine these amplitudes here. So this gives us a little bit better idea of what is in charge of sort of dictating how the natural response looks, how the forced response looks, what the amplitudes are, what the different poles of our transfer function are doing. So now that we have a little better feel of what we're talking about with these systems, we're going to look at a more generalized case for a first order system.